Hey, welcome back to our work on those concyclic points or cyclic quadrilaterals. Here's the work that we were doing before, and I want to give you the solutions to the last 5 problems, number 11 to 15. So let's have a look at the definitions here. 4 points are said to be concyclic if a circle can be drawn through them. There we have the picture right there. And if you join 4 concyclic points, you form this quadrilateral here. So that's what we were dealing with before. And here are our theorems here. A quadrilateral is cyclic if one of the following is true. That is, a pair of opposite angles are supplementary or add up to 180. And we were using that in the first 10 practice problems from Hayes and Harris publications there of the new specialist book for year 11. And then this is the other theorem. One side subtends equal angles at the other 2 vertices. So if you have one side here, DC, and you can prove that alpha and beta are equal, then it's really the converse of the angles in the same segment or angles subtended by the same arc theorem, isn't it? We can say that DC could be an arc of a circle, and these 2 angles would be subtended at points on the circumference. Hey, that's pretty good stuff. So let's go down now and have a look at question 11 from Hayes and see what the solution to that looks like. So you should be building up some skills now. And remember, the first step in a good solution is to draw a well-labelled diagram. Draw a large diagram and label it with everything. So let's read the problem. The non-parallel sides, here we are, of a trapezium. Remember what a trapezium is? They have equal length. Prove that the trapezium is a cyclic quadrilateral. All right, so quite often they give you a diagram, but here, unfortunately, they're not. So let's try and draw the diagram ourselves here. So let's draw a trapezium with opposite sides equal. So here we go. We have this side, opposite sides parallel, sorry. So here, and non-parallel sides are equal. So here we have a trapezium down here like this, and let's call it A, B, C, D. Nice and easy, fairly large diagram there. And these are the parallel sides. And the non-parallel sides, here we are, non-parallel, are equal in length. So we'll do that. That's our basic diagram now. And we've got to prove, I'll put this down more formally now, prove that the trapezium, so A, B, C, D, is cyclic. And I guess, I don't know, we might try to use one of the 2. The opposite angles are supplementary, a pair of opposite angles supplementary, or one side subtends equal angles on the same side. We'll have a look in a minute and see what we think. All right, so we've got 2 parallel lines there, so what could we do? Well, we could say let's use those parallel lines. Remember, the first step is a well-labelled diagram, all the information on it. Then we have a look and look at the to prove line, which we've done. Now we're going to use the first piece of given information to see if we can make a deduction. And let's use these parallel lines. So if we call that angle alpha, so angle DAB equals alpha, therefore we can say angle ADC using the parallel lines. That one is co-interior, and therefore it is 180 take alpha, co-interior angles. And so that's good, but what we need to do is to work up towards the other end of the figure up here to point C, because we've got to incorporate A, B, C and D as the cyclic quadrilateral. Okay, so what are we going to do? Well, there's a little trick here that we could do, and that is to translate, and you might not think of this one, translate AD up to position BX. So if we make it a translation, then we don't change anything, and we move it straight up to, let's say, BX there. So we're translating A to B and D to X, okay, by equal amounts there. Okay, so this then, BX would be equal to BC there, and also we could say angle BXC if we translate it, this will be parallel to this. So translated, AD will be now parallel to BX, and AD will equal BX. So what can we say? Well, angle, here we are, BXC is going to be equal to 180 take alpha, equal to this one here. So that's basically what we're saying here is corresponding angles up there. And also we notice that triangle BXC is isosceles. Okay, BX equals XC under the translation there. BX equals XC. And therefore, angle BCX is also 180 take alpha, base angles of an isosceles triangle. Okay, what can we say therefore? That angle DAB and angle BCX are supplementary. Okay, therefore ABCD is cyclic. Op angles supplementary, running out of room here, and that's as required. We're going to put those things in there as required. Okay, so do you get the idea? That was a fairly hard one. This is a little tricky to do here, translating AD up to the position BX there. All right, have a good look at that one, but we want to follow the same strategy every time so you don't get stuck, or if you get stuck, you know what to go and do, and that's to try and do the basic idea of using each piece of given information in succession and working towards the end of the figure where you're trying to establish something. Let's go on to question 12 now. So question 12 again doesn't have a diagram, so our first step with our strategy there is to draw a well-labelled diagram. So we've got two circles meeting at points X and Y. Let's have a look at that. What does that mean? Two circles, here we are, meeting at points X and Y. Okay, line segment AXB meets one circle A and the other at B. So we've got to draw a line in here. A, and this is X, B. And then we've got line segment CYD. So we're going through here, CYD. We've made a big point there, CYD. And they aren't necessarily parallel either. They might look it, but they're not necessarily. Prove that AC is parallel to BD. Okay, here we are. AC, coming this way, is parallel to BD. So what are we going to put here? The to prove line is AC is parallel to BD. We might think in our mind there, how could we do that? Well, we're going to use alternate angles, corresponding angles, or co-interior angles. If they're in those positions, then we can say the lines are parallel. So we'll have a look at that in a minute. All right, so I reckon what we need to do is, because we haven't got much information, no centres of the circles, well, we've got the quadrilaterals within the circles, so let's make those quadrilaterals up. Now, can you get that idea? That's why we're joining XY, because we can see to use the two circles, we're going to want to use the cyclic quadrilaterals, so they are AXCY and XBDY. All right, so let's have a look. Let's deal with the first one now because we've joined it up. Let's let CAX equal alpha, so angle CAX equals alpha, and we can say CYX, angle CYX equals 180 take alpha. That's this one down here, 180 take alpha, and that's because it's a cyclic quadrilateral, cyclic quad AXYC. Opposite angles are supplementary. Let's go to angle XYD now. We can come in here. Angle XYD, just moving up the figure towards this end a little bit here. That is equal to alpha, sum angles on a straight line. Okay, and what else haven't we used yet? We haven't used the idea of this quadrilateral over here, XBDY, being cyclic. So let's do that. So angle XBD, this angle here, angle XBD will equal 180 take alpha, opposite angles of a cyclic quadrilateral. Okay, cyclic quadrilateral there, XBDY. So we'll put that in, 180 take alpha up there. All right, so where are we? What do we need to do? Well, we're trying to show that AC is parallel to BD. Can we do it? We've moved up this area into this end of the figure, and you've got that angle and that angle. Oh, what do you notice? They add up to 180, so we can write that down. Angle CAX plus angle XBD equals 180 degrees. So we've got those. 180 take alpha and then alpha. Now these are in co-interior positions. So if they're co-interior positions and they sum to 180 or supplementary, then that implies AC is parallel to BD. Okay, as required. We sort of spotted that at the beginning, that parallel lines are established by looking at pairs of corresponding angles or alternate angles and deducing, or co-interior angles, and deducing that the lines are parallel going backwards there. Okay, so did you get that one? That's a little bit of a hard one as well, but go through the strategy, well-labelled diagram, everything on it, state what's to prove, think about how you might do that, and then use one piece of given information after another. And that was hard here, because we really need to establish, because those quadrilaterals were within circles, make it a quadrilateral by joining X and Y and actually work on from there, because there wasn't any other given information. All right, how are you going with all this stuff? Try and stay with the same method every time so that you have a strategy and you're less likely to get stuck. Okay, here we are. Prove that if an exterior angle of a quadrilateral, let's underline that, that's not a bad trick, it's equal to the interior opposite angle. That's what we have to prove. Then the quadrilateral, no, if that's true, then the quadrilateral is a cyclic quadrilateral. All right, well, let's have a look at that and let's draw the diagram. So we've got to have a quadrilateral here. So here's a quadrilateral, any quadrilateral, and we're going to extend the side so this becomes the exterior angle. It's the same as with a triangle. An exterior angle is defined as the angle between any side and the continuation, here it is, or the extension of the side adjacent to it. So okay, that's what we've got here, so let's label it now. A, B, C, D, and we'll call this out here maybe E. All right, so what we're told, if that's true, so that's our given information, exterior angle, so we'll call that alpha and that alpha. Okay, so we've got our given information in there. So we have to prove now ABCD is cyclic. I think this might be an easier one. I think you might be able to see it straight up. But let's go through the usual strategy. We've labelled the last diagram. We've got the given information on it. Now we want to look at the to prove line. How would you generally prove that? Well, we've got the two methods, but this one looks, without angles being subtended, it looks like we'll use supplementary angles, opposite angles of a cyclic quadrilateral as supplementary. We'll probably go there. Now let's use this idea, the given information, first piece, the only piece of information. And so if we use that, we can say angle ADC is 180 take alpha. That's sum of adjacent angles on a straight line. Okay, and so we'll put 180 take alpha in there. And I think the job's done, isn't it? because here you can therefore say angle ABC up the top here, and plus angle ADC is 180. We've just established that. Therefore, ABCD is cyclic. Opposite angles supplementary, what we've just shown there, and as required. It's important to sign off on a proof with as required, or QED, or RTP, or other alternatives. So that one wasn't too bad. It fitted the strategy perfectly, and it wasn't hard to see what was going on there. Okay, we've got 2 more to go, so I hope you've had some success. Let's go down now and have a look. Remember, have a go at these before I show you the actual solutions. Okay, AB and CD are 2 parallel chords of a circle. I reckon we better put those in first of all. So let's draw a large circle. Okay, large well-labelled diagram. And we're going to have AB. A chord is any line joining 2 points on the circumference. And another one down here, parallel. So that's CD. Nothing about their lengths, but we know they're parallel. So put all that in. AD and BC meet at E. AD and BC. Okay, well let's draw AD, line this up, see if we can line that up. AD and BC meet at E. So that's all good. Prove that AEOC is cyclic. AEOC. Now where's AEO? We haven't got O in there. So we're going to have to put the centre of the circle somewhere here. AEOC. Okay. E is that. So it's a funny looking quadrilateral sitting in there. Let's dash it in. AEOC. And so EC. So this is AEOC. AEOC. Yep, so that's okay. They've got O on the other side probably, going AE and O down here somewhere. So that won't make any difference in our question. All right, so let's look at the proof of that. And we've got to prove that that is cyclic. So again, that might be just one with opposite angle supplementary, or it could be subtending angles, because you see here, AE, from A to E to C, that's subtending an angle there. And if we did a line through here, we might be able to use subtending angles on the same side being equal, that sort of idea. All right, so let's have a look at what we've got for a start. So it could be 2 ways of actually proving that cyclic nature. All right, let's have a look. What do we do always? We start with the first piece of information. So let's use the parallel lines here. And I don't know, you might say alpha 1 equals alpha 2. Okay, they are alternate angles. Alternate angles. Go like that. And what else can we see? Well, we had to join these up, so we have got a big cyclic quadrilateral around the outside, A, B, C, D, but probably won't use that. I've also labelled this incorrectly, haven't I? I should have C over here. That'll do as it is at the moment. So I reckon we've got the centre. Okay, let's use that. How can we use the centre? Well, if we join O to C, we'll have an angle at the centre, won't we? So the next indication is the given information says we've got O in the triangle, and therefore we'll use that. So angle AOC, AOC is the angle at the centre, is twice alpha 1, the angle at the centre theorem. Okay, so we'll put that in. That's 2 alpha in there. All right, well that's not bad. Now what else can we do? We could say, angle, what can we say here? Angle AEC could be here, AEC. This one in here. Can we say anything about that angle. I don't know whether we can there at this moment, but we could come down here and say angle EDC. Angle EDC is alpha 3 down here, and the reason for that is subtended by the same arc. Subtended same arc. Okay, and so we've got that. And then what can we say? Angle AEC, that one in there, angle AEC will equal AEC in here. AEC will be equal alpha 2 plus alpha 3 exterior angle of the triangle CDE. Okay, AEC is 2 alpha. Now this is getting all crowded in here. Can you see that we've just done it? In other words, AC subtends equal angles, and they're both 2 alphas, at O and E. Therefore, AOEC is cyclic. Okay, and we can say get rid of that as required, because we've shown it subtends 2 equal angles on the same side. So that's just that one in there. It's very crowded in here. I'll just scrub that out, and so you can see it a little bit better. So we had O there, and we had E here. That's a bit better, isn't it? So what we've just proven, and we'll dash that in there, is AOC and AEC were both 2 alpha. Okay, this one was because it's the exterior angle and those 2 added up. This one is angle at the centre is twice angle at the circumference. Do you get it? It's a bit hard when the diagram got a little bit squashed there, didn't it? We could have done with a larger one. So there's some little tricks here, and it's a matter of really squeezing all the given information. Because they mentioned the centre of the circle, and that formed part of the triangle we wanted to show was cyclic, it's very important that you put that in and then think of theorems that you could use with that. Think of all the theorems related to the centre of a circle. You've got to squeeze all the given information. It'll all be needed at this level. Okay, come down and let's have a look at another one. Now I want you to have a go at each of these before I put the answers up, obviously. So here we have a nice diagram already, fairly large, so you should be able to work on that. RX is the bisector of angle QRT. QRT. That's already marked in for us. Okay, those 2 dots there. I reckon I'll put alpha and alpha. It's easier to refer to angles using Greek letters than angle XRT equals XRQ. Very messy. Prove that PX bisects angle QPX. Well, that's not even in there. We better put that in. PX through there bisects angle QPS. That's what we're after there. So what we're in, look at it. Let's look at our to prove line, because we've got a good well-labelled diagram. We've put in these alphas to remind us that that is a bisector. That's given. We've got to show these 2, this one and this one, are equal. So we look at our to prove line, and there it is, and we can see that's all we have to do is show these 2 angles in here are equal. That's what bisect means. So excuse me, let's just put that back. So you might put in here, that is angle QPX equals angle SPX, just to remind ourselves excuse me, of what we're trying to do. All right, so let's get started, and I don't know. What's the only piece of given information directly is this angle is bisected. So let's use that. So what can we say? Angle QPX also equals alpha, subtended by the same arc. Okay, that's an alpha there. So angle QRS, QRS in here, and you'll see why we're going to do that in a minute. Angle QRS, where are we? QRS, this angle in here, is 180 take 2 alpha. So again, I'm still using this piece of information down here. There isn't much else apart from that. That's 180 take 2 alpha. Okay, now angle XRS, this big angle, this whole big angle XRS, angle XRS, so that's XRS in there. So what's that going to equal? That's going to be equal to 180 take 2 alpha, 180 take 2 alpha plus alpha. Okay, there's 2 pieces there, which is 180 take alpha. Just adding the pieces up there, those 2 pieces. Now SPX, let's have a look. We haven't done anything in here. We need to get in here, don't we? Because we're trying to show that QPX and SPX are the same, so we need that to come to alpha as well. Let's have a look now, and do you see that we do have a cyclic quadrilateral PXRS? Okay, so this angle in that cyclic quadrilateral, so we might put that down, in cyclic quadrilateral PXRS. So that was a bit of a hidden piece of given information there. We've just discovered that because we were looking at this angle up here. In cyclic quadrilateral PXRS, we can say angle SPX must equal alpha op angles supplementary, because the opposite angle was this one down here in that cyclic quadrilateral, and it's 180 take 2 alpha, 180 take alpha, and so the opposite must be supplementary, which is alpha. Therefore we have done it. Angle QPX equals angle SPX equals alpha, and therefore PX bisects QPS as required. Okay, so that was a tricky do, wasn't it? The last piece of information, given information, was hidden, and that was a cyclic quadrilateral hidden in there. Not easy to see that one. So I want you to try and catch the strategy. Remember, large diagram, label it with all the given information, look at the to prove line and see if you can decipher it to how you'll actually achieve that. Then start with each piece of given information and work through. If you get stuck, you've missed a given piece of information, and that's not necessarily given. See, we had to spot that was cyclic there. All right, I hope you're enjoying yourself. It's really a good feeling when you've done that solution and you can sign off and say, hey, that was a good puzzle solved. All right, keep up the good work. Cheers for now. I'll catch you in a later presentation.